Welcome to Non-Euclidean Geometry Lesson 3, Life Without the Parallel Postulate. In this lesson, we're going to use the first four postulates from Euclid and not the parallel postulate. We'll state 6 theorems, we'll prove 5 of them, and one I'll give a reference. And the idea here is that these theorems related to the first 4 postulates from Euclid can be used in hyperbolic geometry, and they also apply to Euclidean geometry. It's just that we're not using the parallel postulate here, and we'll make use of these theorems in the next section when we start talking about hyperbolic geometry. As I mentioned in the intro to this lesson, we're going to use Euclid's first 4 postulates to prove several theorems, and we'll use those results in our hyperbolic geometry work in the lesson after this. And just to emphasize, these theorems still hold for Euclidean geometry. It's just that we're only using 4 of the 5 postulates. Propositions 1 through 28 in Book 1 of Euclid's Elements only require the first 4 postulates. So we're going to assume these results. Now I'm not going to state them here, but I'm going to give you a reference, actually a couple of references. One is Project Gutenberg's first 6 books of the Elements of Euclid, and I'll put this reference is from my book, which I make available. I mentioned this in the very introduction to this set of lessons, but I'll put this also in I'll put a link to this in the information to this particular video. And then there's also an online version of the Euclid's Elements. And I put a reference to this in the information to the previous lesson, but I'll add it here again. So you'll have 2 choices as to where to get these propositions here. We're mainly going to need Book 1, although occasionally we'll refer to things from Book 3. And then I just list here the format here, Book 3, Proposition 9. So I'll do that in some of the proofs. And I may mention what it is briefly, but if you want to actually read the proposition, you need to go to one of these 2 sources here. Okay, so there's also some basic assumptions and axioms that were missed by Euclid. These assumptions and axioms were identified by David Hilbert, a very famous mathematician, and they're listed in a Wikipedia article, Hilbert's axioms. I'll put this reference in the information to this video also, and we'll make use of some of these too, and I'll mention them as we use them. They're mostly pretty obvious, but we need to state them. So just some groundwork here before we actually get into the details. The theorems that we're going to talk about in this lesson are mostly related to the Secchieri quadrilateral, which we introduced previously, and I thought I would just give you a recap here before we get into the theorems themselves. So we have a picture here of the Secchieri quadrilateral. The bottom here is called the base, so AB is the base. Then AD and BC are called the arms, and they're at 90 degrees with the base. So this little square in here means 90 degrees. And then the top segment, top leg of the quadrilateral is called the summit, and then the angle here at D and C are called the summit angles. And we also define the Secchieri quadrilateral to have the arms are of equal length, which I mentioned here. And we're going to prove that the summit angles are not obtuse, so they're less than or equal to 90 degrees if we remove the parallel postulate. So in the case of Euclidean geometry, though they will be 90 degrees, but when we get into hyperbolic, they'll be less than, these summit angles will be less than 90 degrees. But we'll get to that in the next lesson. So let me repeat one more time just for emphasis here. The theorems in this lesson are derived from the first four postulates of Euclid, minus the parallel postulate. We don't use that here. And then whatever propositions can be derived from those first four postulates, which are the first 28 propositions in Euclid's book number 1. We make use of those and we derive theorems from them. Those theorems apply to Euclidean geometry, but they also apply to hyperbolic geometry, because hyperbolic geometry, as we'll see in the next lesson, is defined by the negation of the parallel postulate. So anything we can prove using the first four postulates from Euclid and also apply to hyperbolic geometry. Okay, so that said, let's look at the first theorem here. The summit angles of the Secchieri quadrilateral are equal. I have proof here, and I want to put the Secchieri quadrilateral here on the bottom. So we're going to make use of the side angle side principle from book 1, proposition 4 from Euclid's Elements. We'll also make use of side, side, side. So side angle side is just saying if you have two triangles and they have a side, an angle, and a side that are equal across the two triangles, then they're congruent. That means they're exactly every angle and every side of the two triangles are equal. And then there's another congruence proposition, side, side, side. So two triangles have the same side lengths, then they're congruent, meaning in this case, all their angles are also equal. So let's look at this first one here. We have triangle ABC, so ABC, and we have triangle BAD. So if you notice that ABC has an angle here, which is 90 degrees. It has a side, and it has a base, AB. And then BAD has the same angle here, 90 degrees. And this side, by definition of a Secchieri quadrilateral, AD is equal to BC. And then the two triangles share the same base, AB. So by side angle side, ABC is congruent to BAD. And what that implies is that AC, this long side here, is equal to BD. Okay, so that's the first part of the theorem. So these two diagonals are equal. And then we make use of the side, side, side congruence principle, because we have triangles A, D, C, so this upper one here, and triangle B, C, D are congruent. But if by side, 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 because we just showed that the diagonals were the same, and we know that they both share the same summit, same top here, and these two arms are the same. So these two triangles are congruent by side, 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 but then that gives us what we need, because it says that this angle D is congruent to this angle C, and that's what we wanted to prove, that the two summit angles are the same. Theorem number 2. The line segment between the midpoints of the base and summit of a Secchieri quadrilateral, so in other words, if N is the midpoint here of the summit and M is the midpoint of the base, then this line here is perpendicular to the base and the summit. So NM is perpendicular to AB, and NM is perpendicular to DC. So that's what we want to prove. By side angle side, triangle ADM is congruent to BCM. That's because these two sides here, AD and BC, are the same by the definition of the Saccheri quadrilateral. AM is equal to MB because we've defined M to be the midpoint, and these are both 90 degrees by the definition of Saccheri quadrilateral. And so by side angle side, these two triangles are the same, and then that means that this angle here is equal to that angle here. This angle here, alpha prime, is equal to gamma prime, and also the diagonal here, this DM, is equal to CM. So we have that. Now we're going to look at these triangles, kind of the upper triangles here, this one here and this one here, and they're congruent by side, side, side. This side is equal to this side. We just proved that. N is the midpoint, so dN is equal to NC, and then they share a common side here. So dNm is congruent to CNm, and that means that x equals y, beta equals delta. And since DC is a straight line segment and x equals y, the x plus y has to equal 180, which means that both x and y are 90. Then we have the same thing on the bottom here because we've shown that alpha prime plus beta equals delta plus gamma prime, which I've written here. And since these two together equal these two together, and this is a straight line, they have to sum up to 180, which means that this angle here, alpha prime plus beta equals gamma prime plus delta equals 90. So in other words, NM is perpendicular to AB, which is what we wanted to prove. Theorem 5, the summit angles of a Saccheri quadrilateral are not obtuse. In other words, they're less than or equal to 90 degrees. Proof is as follows. Consider the Saccheri quadrilateral ABC shown below, this thing here. If the summit angles were obtuse, the sum of the angles of the quadrilateral would be greater than 360. So we'd have these two angles down here are 90, and then if these are both greater than 90, then the sum of these four angles at A, B, C, and D would be greater than 360, but the sum of the angles in the triangles A, B, C, and ADC which equal the sum of the angles in the quadrilateral ABC, would be greater than 360. Thus, the sum of the angles in either ABC or ADC would need to surpass 180, but we know that it's not possible because of theorem 4, which we proved on the previous slide. Therefore, the summit angles cannot be obtuse. They must be less than or equal to 90 degrees. The following theorem applies to quadrilaterals that have right angles at their base, as I'm showing here, but not at the summit. In fact, the summit angles are different. So this is not a Sakiri quadrilateral, but we can still prove something about this. So given a quadrilateral with right angles at its base, if the edges, the arms here, AD and BC, extending from the base are unequal, which they are in this case here, then so are the associated summit angles. And conversely, the greater the summit angle lies opposite the greater arm. So alpha is the bigger of these two angles here, and it lies opposite the longer or greater arm of greater length. And then, of course, the smaller angle lies opposite the arm of lesser length. So we need to prove this in 2 parts, and we'll do that in the next couple of slides. The theorem on the previous slide was basically an if and only if theorem, so we need to prove it in both directions. Let's start with the case where AD, the arm here, AD is less than BC, and we select a point E here such that AD is equal to EB. The quadrilateral ADEB is by definition a Sakiri quadrilateral because we have 2 right angles here and here, and then this side AD is equal to AEB by definition of where we placed E here. And given that by theorem 1, we know that the angle ADE is equal to the angle BED. So we have this here. Since the line segment DE subdivides ADC, we know that ADC, this bigger angle here, is bigger than ADE. That's one of the assumptions that David Hilbert, discovered that was missing from Euclid's Elements. So it's pretty obvious, right? If you have an angle and you dissect it, not necessarily in half, but if you just dissect it, then the overall angle here is going to be bigger than either one of the angles that are left from the dissection. So then we have this one here, this inequality here. We're not done yet. We need a little bit more. This is where we use the proposition 16 from Euclid's Elements. And it's a little bit complicated here. It says if in any triangle, if one of the sides is produced, then the exterior angle is greater than either of the interior and opposite angles. So let's see what that means in terms of the triangle ECD. The exterior angle they're talking about here is this angle here, DEB, the angle right here. And what they're saying in this proposition is that this angle is bigger than either of the opposite interior angles. So DEB is greater than ECD, and it's also greater than CDE, but we don't need that part. So we have that BED, this exterior angle to this triangle, is greater than ECD, which is the same as BCD, just written here. Then we can just put together these equality and inequalities here. We have that ADC is greater than ADE, so we prove that up here, and ADE equals BED, and then BED is greater than BCD. So in other words, ADC is greater than BCD. And that's what we wanted to prove going in one direction. So the if the summit angles are unequal, which they are, the angle of greater measure lies opposite the arm of greater measure. So we started out with AD being greater than BC, and we showed that this angle here was bigger than this angle here, and so the larger angle is opposite the larger arm, which is BC. So now we need to go in the other direction and assume the angles, are unequal. One's bigger than the other, and then show that the arms, the opposite arm to the larger angle is the bigger arm. So we'll do that in the next slide. Okay, now we want to go in the other direction. We'll assume the summit angles of the quadrilateral down here, ABCD, are unequal without loss of generality. And as shown in the figure here, let's just assume that ADC, which I've labeled as angle alpha, is greater than BCD. Okay, so the arms AD and BC cannot be equal, since that would imply the summit angles are equal by theorem 1. Right? If these two arms are equal, then we have a Secchieri quadrilateral, and theorem 1 says that alpha equals beta. So we just assumed that wasn't the case. So AD cannot equal BC. So either we have AD is greater than BC, or BC is greater than AD. The former inequality cannot be true, since that would imply that BCD is greater than ADC, and that's what we proved in the previous slide. So this case is excluded. So it must be that BC is greater than AD. Thus, when the arms are unequal, the greater one lies opposite the greater summit angle. In other words, the greater angle here is on opposite from the larger side here, and of course the smaller angle is opposite the smaller arm, which is what we wanted to prove. Okay, so that's it for this lesson. Next lesson we'll start on the definition of hyperbolic geometry, and we'll make use of these theorems here, because recall these theorems only depend on the first 4 postulates of Euclid, which we're going to carry over in the hyperbolic geometry, and then we'll negate the 5th postulate and replace it with something different, and that'll give us a basis for hyperbolic geometry, which is what we'll talk about in the next lesson.